Welcome on the day 12 of this online course Physics with Scilab. Today I will talk on the Fourier series, calculating the Fourier coefficients and plotting Fourier series using Scilab. Joseph Fourier in 1807 proposed that a periodic waveform f of x could be broken down into an infinite series of simple sinusoids, which when added together would construct the exact form of original waveform. For example, if we consider the periodic function f of x is equal to f of x plus 2nl, where 2l is the period of the waveform and n is the integer, then the Fourier series for the function f of x can be expressed as f of x is equal to a0 plus summation n is equal to 1 to n an into cos of n pi x by l plus n is equal to 1 to n bn sin n pi x by l. Here a0, an and bn are real and are called Fourier trigonometric coefficients. So a0 can be calculated as a0 is equal to 1 by L integral from minus L to L f of x dx. An is equal to 1 by L integral from minus L to L f of x cos of n pi x by L into dx. And Bn is equal to 1 by L integral from minus L to L f of x sine n pi x by L into dx. Thus, the Fourier series is an accurate representation of any complex periodic waveform which consists of the sum of sinusoids at the fundamental and harmonic frequencies. We can also generate any sinusoidal periodic waveform by an appropriate combination of sinusoidal functions. For example, we can use sine waves to make the square wave. So if we start with this sin x waveform, then if we add the sine 3x by 3 to this waveform, then we will get this kind of waveform. So you can see how it starts to look like the square wave. Again, if we add sine of 5x by 5 into this waveform, then it is getting better. When we add infinite number of such a sinusoidal harmonics, then we would have a square wave. Now we will see the calculations of the Fourier coefficients and the plotting Fourier series in the Scilab. First, let's see the calculation of Fourier trigonometric coefficients a0, an and bn. So here is the program I have already written. Funcprod is the command to stop the message of warning of redefined function which appears when we execute the program. Then the command clc for clearing the console before the execution of program. Then the function is defined for calculating Fourier coefficients a0, an and bn. Therefore, in square bracket a0, an, bn is equal to function fcoef with the three variables L for the half period of the periodic function, f and n is the number of terms to be included in Fourier series. Here a0 is given by the integral 1 by L into minus L to L f of x dx. For integration, I have used here int function with the arguments lower limit, upper limit of integration, then the integrand function and the absolute error required on the result. Then the function a equal to f1 of xf, it is the integrand for the calculation of the coefficient an. So an is equal to 1 by L integrand from minus L to L f of x into cos n pi x by L into dx. So same is appear over here. Similarly, the function b is equal to f2 of xf is the integrand for the calculation of the coefficient bn. So it is equal to f of x into sine of n pi x by L. The integration for getting the values of the coefficients an and bn. So it will give me the values of nth coefficient of Fourier series. But I want the values for this coefficient from 1 to n. So therefore I use the for loop for I is equal to 1 to n. Then the steps I want to repeat for 1 to n. I will bring into this for loop and replace n by I. So now this program is ready for the calculation of the Fourier trigonometric coefficients. So save and execute. To execute this program, I have to provide the arguments for this fcoef function. So that are L, N and F. So L I will take 5, N 5, and the function f is defined by, so c is equal to f of x comma c is equal to simply x. So L is equal to 5, N is equal to 5, and f is the function, c equal to x. So this will give the values of Fourier trigonometric coefficients. So here the values of a0 and an are 0, and only we have the values of bn. Thus we can calculate the coefficients of Fourier series using this program. Now let's see the plotting of Fourier series. To plot the Fourier series on the graphics window, so I have written the program. Here only I have changed the function f COEF to F plot because here I want to plot the Fourier series. Rest of the steps I have kept similar. Only I have added the function Fourier series Fs is equal to solution of x, for where Fs is equal to a0 by 2. Then for summation I have used the for loop I is equal to 1 to n. Then the Fourier series will be equal to Fs, that is a0 by 2, plus an of I into cos I pi x by L, plus bn of I into sin I pi x by L, where I is from 1 to n. Then and the variable x against which we are plotting the Fourier series, I have taken from minus 5 times L to plus 5L with the step size of zero point 0.1. Then plot 2D function plotting the Fourier series against the x. Now this program is ready for the execution. Save and execute. First I will have to define the function. Put c is equal to f of x, where c is equal to x. So this is the function. Then for plotting the Fourier series, we have defined the function fplot, for which argument are L, N and F. So L I will take 5, N 5, and the function f of x. Now enter. So these are the Fourier trigonometric coefficients, and this is the graphics window. So I will dock this graphics window into the console so that we can simultaneously see the Fourier coefficients and the Fourier plot. So here in the sawtooth waveform, this part is not that smooth. I will try for another values of n. So again the same function. So instead of 5, now I will take 20 and enter. Now it is more smooth than the earlier figure. Now I will use 50. It is again more smooth. So in this way we can increase the value of n. More and more perfect Fourier plot we can see. Now we will take 100. So this is a perfect sort of waveform. The program we have seen can be used for calculating the Fourier coefficients and plotting the Fourier series for the periodic waves which are defined by the one function over a complete period. As in the case of sawtooth wave, here function f of x is equal to x, and it is same for the complete period from minus L to L. But if the periodic wave is defined by two separate functions for the first and second half periods. For example, square wave shown in the second figure defined by function f of x is equal to -1 for minus L to 0 and +1 for 0 to L. Then for this we cannot use the same program, therefore we need to modify it. So here is the modified program for such cases. Here function plot has a 4 arguments L, N, F3 and F4. L again is the half of the period, N is the number of terms required in the Fourier series. F3 and F4 are two functions defined for two halves. The coefficient A0 is calculated by this formula: 1 by L in bracket the first integral from minus L to 0, the integrand is the function f3, plus the second integration for 0 to L, the integrand is the function f4. In the program, I have used the function integrate for the integration instead of intg that we have used in the earlier program. The argument are the function f3 for first half of the period, the variable x of the integration, limits minus L to 0 for first half, and the next argument absolute error required in the integration. Similarly, the second integral, here integrand is the function f4 and the limit of integration is from 0 to L. Similarly, for the coefficients an and bn, the coefficient an is equal to 1 by L into the bracket the first integral with the integrand f3 of x into cos n pi x by L. The limits of integration are from minus L to 0, plus the second integral, the integrand is f4 into cos n pi x by L. Limits are from 0 to L. Similarly, bn is equal to 1 by L into the bracket first integral, the integrand is f3 into sin n pi x by L. Limits of integration from minus L to 0, plus the second integral, integrand is f4 into sin n pi x by L. Limits of integration are from 0 to L. Here I want this coefficient for the values of n from 1 to n. Therefore, I have used here for loop. To get the Fourier series, the function fs is equal to SOL of x, where fs is equal to a0 by 2, which is the first term in the Fourier series, and for sum over n terms of an and bn there is a for loop, same as we have used in the earlier program. The values of x are taken from minus 5 times L to 5 times L with the step size of zero point 0.1. Plot 2D function will plot the resultant Fourier series against x. So now we will try this program. So first I will dock this graphics window into the console so that simultaneously I can see the values of Fourier coefficients and the Fourier plot. So to execute this program, I have to first define the functions f3 and f4. So f3 of x, I called it as a, comma, where a is equal to 1. Now another function b equal to f4 of x, comma, where b is equal to, I think, -1. So these two functions define the square waveform. Now to plot the Fourier series and to get the values of the Fourier coefficient, I will call the function fplot. So I take the value of L2, the number of terms in the Fourier series. I take 5 and f3 and f4 functions as defined above. So enter. So this is the required Fourier plot for the given function. So here are the values for the Fourier coefficient. You can see an and a0 coefficients are 0 because the given function is odd. Now we will plot for more number of terms in the Fourier series. So same function f3, same f4, fplot function. So now I use n is equal to 30. So now this square waveform is more better than earlier. So to get more perfect square wave, now I take n is equal to 100. So it is more better than earlier. So in this way, by increasing the number of terms in the Fourier series, we can get better and better Fourier plot. Now we will try for some other waveform, which is defined by the function f3 equal to, suppose, x for the first half of the period and the function f4 is equal to minus x for the second half of the period. So number of terms in the Fourier series is suppose 20. Now this is the triangular waveform. Let's try for some other function. Let f3 is equal to 2 sine x minus 2 sine x.
and the function f4 is 0 in call the plot function. This shows the half wave rectified wave. So in this way we can plot various waveforms using different functions. This is all for today.